Okay, this video is our third example of applying just very straightforward combination and permutation techniques to different areas of statistical physics. Incidentally, if you just found us on YouTube, if you can go to the website at digital-university.org, you'll see that we have a whole series of videos dealing with combinatorics and probability, and we have different combination problems, different permutation problems, and then with that background we went on to develop generating functions and how we could use generating functions to solve more of the difficult combination and permutation problems. And again, you can find all the videos at digital-university.org. Here in this video, we want to consider this problem. Suppose that we have a k number of identical objects, and we have n boxes to place them into. And we actually have more boxes than objects, and we can only place one object in each box. So obviously each time we do this, we're going to have some empty boxes left over. The question is, what is the probability of any particular distribution? And this type of problem is representative of Fermi-Dirac statistics, where, for example, each one of the identical objects could be an electron, and each one of the boxes could be a different energy level. Each box or each energy level accommodates only one object. So before we answer this question, let's consider first this kind of a problem. Suppose that we have not identical objects, but suppose we had k number of different objects, and we have n number of boxes, and we're going to put one object into each box, and we have more boxes than objects, so obviously each time we do this, we're going to have some empty boxes left over. But if we now have different objects to put in these boxes, how many different ways can we do it? And to answer that question is pretty straightforward, really. We just use the counting principle. Say that our first task, T1, is to select object A and put it into one of the boxes. And then how many ways can we do that? Well, we have n empty boxes available for us, so there are n choices. Then our second task, once this is completed, is to select object B and put that into one of the empty boxes. Now, A has already occupied a box, so for object B we have n minus 1 empty boxes available. And then let's say our task 3 is to select object C. Now we have n minus 2 number of boxes, of empty boxes available to place this object into, so we have n minus 2 number of choices. And let's say that task T4 is to select object D. Now we'll have n minus 3 number of empty boxes available, or n minus 3 number of choices. So let's say that we keep proceeding like this until we get to the last object, object K. Now how many empty boxes will be available for it? Well, let's see how this pattern goes. Here, for the second box, it was n minus 1. For the third, or for the second object, it was n minus 1. For the third object, n minus 2. The fourth object, n minus 3. So clearly, this number is one smaller than this one. So we'd have n minus k minus 1. Here we're having fourth object n minus 3, kth object n minus k minus 1 number of choices, or this number of empty boxes. Or this would be the same thing as, try to keep things in focus now, this would be the same thing as n minus k plus 1. So let's write it like that. N minus k plus 1. Okay, now the question that we had was, if we're going to place one object in each box, there's more boxes than objects, what's the total number of ways that we can do that? And the answer is, using the counting principle, it is the total number of ways that you can perform task 1 times the total number of ways you can perform task 2 times the total number of ways you can perform task 3 times the total number of ways you can perform task 4, all the way down to performing task k. The number of ways of performing task 1 is n. The number of ways of performing task 2 is n minus 1. This was n minus 2. This was n minus 3, all the way down to n minus k plus 1, which we derive from here. So this expression right here tells us then the total number of ways that we can place k different objects into n boxes with one object going into each box, and we have more boxes than objects. Now let's look at our expression here and try to keep it in focus while we do so. Okay, here we have n times n minus 1, so it decreases by 1. n minus 2, it decreases by 1 again. n minus 3, it decreases by 1 again. And it keeps going like this, keeps decreasing by 1 until we reach this number. Now, if we wanted to continue this series, what would be the next number? Well, the next number would have to be 1 smaller than this one. So it would have to be n minus k. And the next number would be one number smaller, so it had to be n minus k minus 1. And if we continue the pattern like that, we'd keep going, getting smaller by one number, until finally we just reached the numeral 1. Now, if we multiplied this, and this right here tells us the total number of distributions we can make, if we multiply it by this, we can do that, providing we also divide it by this expression. So let's just do it like this. So what we're doing is we're taking our original answer and we're multiplying it by 1. This divided by itself. Now when we do that, in the numerator we start with n, and we get progressively smaller all the way down to 1. So the numerator is just n factorial. And down here in the denominator, we start with n minus k, and we keep going progressively smaller by 1 until finally we reach the numeral 1. So the denominator is n minus k factorial. So this expression right here tells us the number of ways that we can place k number of different objects into n number of boxes. One object per box, and we have more boxes than we have objects. That's n factorial divided by n minus k factorial. And if you have watched the earlier videos, you know that we denote that with this symbol, P and K. So this tells us then the total number of distributions, or the total number of ways that we can place k objects into n boxes, one object per box. And there's more boxes than objects. Now, if we had the reverse situation, where there were more objects than boxes, then in that case, the total number of distributions would be like this, pk over n. Okay, well, let's go back now and consider our original problem, and that was, first let's make some room. Now, the problem that we posed at the beginning of the video was we had k number of identical objects, not different objects. So let's see, let's just say that our objects are like this. These are all identical objects now. And we have k number of them, and we have n number of boxes, and we have more boxes available than we have objects. And we place only one object in each box. So each time we do this, we're going to have some empty boxes left over. But now, if we have identical objects, how many different ways can we do this? And to get a grip on that, let's just review what we did when we had different objects. When we had, say we have this kind of a situation. So here we have, for example, two different objects and three different boxes to place them into. How many ways can we do it? Well, we just figured that out. It's P and K, or P32, which is 3 factorial over 1 factorial, which is 6. And here are the 6 different ways it can be done. We have BA, AB, or we could have AB or BA, or try to keep these in focus, AB and BA. Okay, well now what happens then if, instead of having different objects, these two objects are the same? So this would be AA and AA. So these distributions would be identical, which we've shown right here. Likewise, these two different distributions now would be identical, AA, AA, which we've shown right here. And likewise, this would be AA, AA, so these two different distributions would now be the same distribution, shown right here. So now, when we have identical objects, and we place one object in each box, and we have more boxes than we have objects, now the total number of ways of doing it is not this expression. Instead, it is this expression. And if we think about it, that should make sense, because, for example, what this means is, here we have n number of boxes. We're going to select k of them, and when we make our selection, the order doesn't matter. And that makes sense, because let's say that we decide to choose 1 and 2. Or we could choose 2 and 1. It'd be the same result, AA. We could choose 2 and 3, or we could choose 3 and 2. The result would be the same, AA. So the order in which we make our selection doesn't matter, and of course that's exactly what a combination is. We could select box 1 and 3, or we could select box 3 and box 1. So the order doesn't matter which we select the boxes, and that's exactly what it tells us here. So, and also let's consider this. This is a particular distribution. This is a particular distribution. This is a particular distribution. Now, our problem was, try to keep things in focus, if we have k number of identical objects to put into n distinct boxes, one object in each box, our question was, what is the probability of any particular distribution? Well, first of all, the number of ways that any distribution can occur is just one. So let's write this down. Well, first of all, let's write this down, that the total number of distributions in this case is C n k. We've just shown that. Now, the number, so this is the total number of distributions. Total number of possible distributions. When we have identical objects to place into different boxes, one object per box, and we have k of them, k objects, and n boxes, more boxes and objects, the total number of distributions is this. Now, the number of ways to obtain any particular distribution is just one. So, what is the probability to obtain any particular distribution? The number of ways you can do it divided by the total number of distributions possible, or that's just going to be 1, divided by this. And so that is the answer to our problem. And of course, this would just be equal to k factorial times n minus k factorial divided by n factorial. Remember, for that, this gives us n factorial over k factorial times n minus k factorial. That's what this is. Here, to get the probability for any particular distribution, it's the reciprocal of this, so we're going to get this expression. Okay, that's all we had to say for this video. It was actually quite simple because of this. The number of ways of attaining any particular distribution is 1. But remember from our earlier videos, if we had more complicated situations where we had different objects, say this is object 1, a different object 2, a different object 3, a different object 4, and we had more objects in boxes, and we could place multiple objects in each box, then the number of ways of obtaining any distribution wasn't 1. In that case, it was the total number of objects, k, divided by the number of objects in the first box times the number of objects in the second box, these factorials, times the number of objects in the third box, like this. Again, we did this in our very first video. That is the total number of ways of obtaining any particular distribution in that scenario. In our problem, it was simple because the number of ways of obtaining any particular distribution is just 1. Okay, that's it for this video. Hope it was worthwhile for you. Come back and join us for some more videos, and we'll try and solve some more problems.